Welcome to our second bite-sized webinar, this time on embodied carbon at the Forge. I'm Helen Hough, Head of Sustainability at Bryden. The Forge in central London is the first private sector building completed using the platform approach from building design to delivery. It's a development of two 9-storey office buildings, 14,000 square metres, close to the Tate Modern, a collaboration between Landsec, Bryden as architects and engineers, and Easy Space. These buildings are built around an internal courtyard. The project was completed in March 2023 and is the world's first major commercial development to be designed using a platform approach to design for manufacture and assembly, P-DfMA. Bryden has developed P-DfMA over many years. Taking lessons from the manufacturing industry and applying them to construction, DfMA is based on the understanding that comparable built assets share many common characteristics in the dimensions and requirements of their core elements, such as floor-to-ceiling heights, for example, or how to connect vertical and horizontal structural elements. Similar to how flat-pack furniture uses standardised parts and assembly techniques as integral elements in a wide range of products, DfMA designs buildings using standardised kit of parts that can be effectively combined while still producing highly customised structures. The project was awarded funding through the Innovate UK Transforming Construction Challenge Fund, initially as an R&D project to test construction platforms, and then as a demonstrator project to apply the learning from the R&D to a real-world project. To accomplish a 9x9 metre grid, which is typical of London offices, the building uses a common, repeatable components developed for Platform 2. This carrier frame then allowed supply chain partners, particularly the M&E and facade, to develop their own complementary elements. These would leverage the accuracy and consistency of the main superstructure to enable more productive ways of working. DfMA focuses on the optimisation of each standardised element, knowing that when they are used many times, they will repay hugely. Optimising a standard beam so that it requires minimum amount of steel, or reducing the depth of the floor slab to minimise the amount of concrete required, delivers substantial reductions in both carbon and cost when applied to entire sites, or even more so over multiple sites. The project's landmark status comes as a culmination of many years of thinking and development, and the first proof point of an approach to designing construction that has the potential to transform construction. In doing so, the Forge delivers a raft of benefits to the built environment and, in particular, through significant reductions in embodied and operational carbon. As a result of optimisation, automation and standardisation, the DfMA approach increases productivity while reducing carbon, both embodied and in operation, construction time and cost. It's the first commercial development in the UK to be designed in line with the UK Green Building Council's Net Zero Carbon Buildings Framework. It was one of the pioneering projects of design for performance initiated by Better Buildings Partnership and has since achieved a 5-star NABERS UK Design for Performance rating, with ongoing energy monitoring currently being undertaken. In this bite-sized webinar, we will focus on the embodied carbon achievements of the project. Embodied carbon calculations were undertaken by Cundall on behalf of Landsec. Cundall updated the calculations at every stage of design, from business as usual design in 2018, the incorporation of DfMA by Bryden in 2019, through to completion in 2023. The business as usual scheme was a traditionally designed office building with a steel frame and a concrete slab, a large basement between both buildings, and a gas-fired heating system with fan coil units for Block A and a VRF system for Block B. The design evolved to incorporate DfMA following the planning approval. The calculations consider the whole life of the building, from the product stage, transport and installation to site, the annual energy and water consumption, how the building is used and any replacement for components or elements, and finally, at the end of life of the building after an expected 60 years. The result showed that the upfront carbon, stages A1 to A5, which is the carbon used on day 1 to manufacture the materials, transport them to site and install them, was reduced by 39% between the business as usual scheme and the as-built performance of the DfMA scheme. This is a significant improvement which can be attributed to both the use of DfMA and the low carbon specification of materials. The breakdown on a whole life basis, so modules A to C, excluding the operational energy and water, which is the embodied carbon both on day one and ongoing across the next 60 years to account for any maintenance and repairs and what happens to the building or components at the end of its life, shows that the superstructure, external wall including the curtain walling, and the MEP to be the predominant contributors to the whole life carbon. These are the main areas where lessons can be learned on how to reduce embodied carbon on day one and reduce the impact over time as materials and components come to their end of their useful life. There's a perception across the industry that operational carbon is more significant than embodied carbon. Our results show that the operational carbon is expected to be around a third of the whole life carbon over the next 60 years. This operational carbon is based on NABERS Design for Performance modelling and is monitored during the building's first year of occupation. At 2/3 of the whole life carbon of a building, embodied carbon is critical to address in the early design stages and provides the greatest opportunity for overall carbon impact reduction. The key findings for upfront carbon are: the substructure used 50% cement replacement, used recycled aggregates from the demolition on site and procured the concrete locally. In addition, the basement volume was reduced, which minimised the excavation and material usage, resulting in a combined 46% improvement compared with the business as usual scheme. The DfMA approach significantly reduced embodied carbon of the superstructure. This is due to the reduction in steel weight. Once the concrete mix was taken into account, the use of 40% GGBS and local procurement, and 26% recycled steel, the savings are around 60%. The embodied carbon within the facade increased compared with initial projections. This is partly due to the anodised finish of the aluminium frame curtain walling, couldn't be altered due to the existing planning permission, and partly because the facade was manufactured in Poland, a country with both many transport miles and an electricity grid predominantly fuelled by coal. The internal finishes and walls perform well due to the limited quantity of materials used. The false ceilings were omitted to reduce materials needed. The curtain walling is self-finishing inside of the external walls. The building is largely open plan, reducing the number of internal walls required. And finally, the raised flooring is reused from an existing building. The materials specified for the internal wall include recycled materials, reducing their embodied carbon. Finally, the DfMA approach has optimised MEP systems using modular prefabricated units, which reduce the amount of material used. When comparing our results with LETI benchmarks, this is not apparent, and it's becoming clear across the industry that the LETI benchmarks for MEP are likely underestimated. When reviewing the building against benchmarks for whole life carbon, including the LETI extrapolated targets, the buildings perform well against what was considered to be a target back in 2020. Again, the buildings hit the current GLA benchmark, albeit the facade performance is higher than the GLA expects. However, were this a building to be designed now to achieve the current LETI or REBA 2030 targets, further learnings need to be taken forward. So what are the lessons learnt? For the superstructure, the platform system reduces embodied carbon. Further development can be undertaken to explore reducing whole life carbon further. Ideas could include replacing confloor with a less processed material which can act as form wet, adjusting the concrete mix to be flowing rather than self-levelling, which would reduce the cement content, and exploring the use of low carbon concrete columns instead of steel ones. For the facade, there are opportunities to improve the embodied carbon of facades, including finding alternatives to unitised and curtain walling systems and their materials. For the cladding, elongating a material or component's lifespan may increase the day one carbon, but over the lifetime of a building, the whole life carbon can be minimised, where replacement cycles are reduced. In aluminium procurement, minimising transport miles is important for materials. However, the country of origin is also important for materials and components which are heavily manufactured, such as curtain walling. Sometimes the additional transport miles might offset the manufacturing emissions in countries with greener energy grids. For the substructure, omitting basements should be a starting point of projects. Learning from the reused raised floor, reusing existing materials both from demolition on site, but also local existing buildings which are undergoing renovation or demolition, reduces emissions. The industry needs to develop a material database to assist with this, but the more demand, the quicker it will happen. And finally, for MEP, the LETI benchmarks are likely underestimated for high-end offices. To meet the LETI benchmarks, this means every other building element needs to perform better to offset the impact of MEP. MEP calculations are still in their infancy compared with the rest of the building, meaning more research and data collection is required to create robust calculations and benchmarks. MEP has a short lifespan compared to other elements, and as such it's even more important to consider the whole life impact of services alongside the operational carbon impact. Thank you for watching. Please get in touch to continue the conversation.